Chapter 8 is about testing, and so the first thing that we're going to look at in 8.1 is the introduction to this, which is how to set up and do a statistical test. We will be doing these tests in 5 steps. Now, the book does the 5 steps as well, but it does not necessarily call it step 1, step 2, step 3, step 4, step 5. But to me, it's just more organized, and so that's the way that I do it. Now, for every statistical test, we will do these 5 steps. So step 1 is stating the hypotheses. Step 2, the test statistic. Step 3, finding the probability. Step 4, we will either reject or fail to reject. And step 5 is your conclusion. Now, we're going to talk about each one of these steps, and then we're going to proceed to do them. Now, why do we do a hypothesis test? Well, in a hypothesis test, you're given a population average, such as if I told you the average age of NOC students is 35 years old. Then what we're going to do is find a sample mean. If the sample mean is far enough away from the given population mean, then you will reject the given population mean and conclude that it has changed. So what I'm saying here is if somebody told you this, that the average age of NOC students is 35, you might go, I don't think that's correct. So let's run a statistical test to see if it is. Then what you would do is go through all those steps, and then we would either reject it or fail to reject. So that's what we're going to start looking at. So let's first look at what step 1 is. And we're going to learn how to do step 1. Now, step 1 is stating your hypotheses, and you have 2 of these. H sub 0 is what we call the null hypothesis, and this is where mu is equal to some number. So in our example, we would say that the null hypothesis is that the average age of NOC students is 35. And the null hypothesis will always be a statement of equality. It will say equals. Now, this is the statement that is under investigation. We think that this is a population mean that is true, has been true, or may still be true, but this will be given to you in the problem. However, we think it's different or it has changed. The alternate then, when you state the alternate, you think it has changed, and you're going to make a statement of what you think the change is. Now, in this case, I would assume that most of you think that the average age of NOC students is less than 35. So in this case, we would use less than. The alternate is H sub 1, and it will be a statement of inequality, so it could be less than 35, or you may do a problem that you use greater than, or you may do a problem that you use is not equal to. Now, this is the statement that you will adopt or embrace when the evidence is strong enough to support that or to reject the null. So we either think that the population mean is smaller, which would be less than, larger, greater than, or just different from. And this is determined in the question part of the problem. So let's look at an example from the book, and what we're going to do is set up the hypothesis testing. So in your book, and I'm getting my book as well, I want you to turn to page 424. And we're going to look at problem number 18. It reads, Consumer Reports stated that the mean time for a Chrysler Concorde to go from 0 to 60 miles per hour is 8.7 seconds. So we're going to look at part A, and it reads, if you want to set up a statistical test to challenge this claim, what would you use for the null? Well, the null is what is given. And so the null hypothesis, they tell us that the average is 8.7 seconds. So that would be my null hypothesis. All right, let's look at part B. The town of Leadville, Colorado has an elevation over 10,000 feet. Suppose you wanted to test the claim that the average time to accelerate is longer in Leadville. What would you use as the alternate? All right, well, if we think it's longer, then we're saying that the average speed would take longer or would be greater than 8.7. And then we're going to look at C. and it reads, suppose you made an engine modification and you think the average time to accelerate from 0 to 60 miles per hour is reduced. So our alternate in that case is we're saying that we think the speed is reduced or less than 8.7 seconds. So what I want to do in the next example is I want you to turn to page 425, and we're going to look at number 23. Now eventually these are the types of problems that you will be doing step 1 through step 5. But all we're going to look at right now is step 1. So I'm going to write step 1. I know I'm going to write the null will be mu is equal to some number. And then the alternate will be mu, and I don't know if it'll be less than, greater than, or not equal to. So in problem number 23 on 425, it says nationally about 11% of the total U.S. wheat crop is destroyed each year by hail. An insurance company is studying this damage in claims in Weld County, Colorado. A random sample of 16 claims is given. They give me the sample mean, assume it's normally distributed, and they give me sigma. Now, when you're setting up the null and the alternate hypothesis, typically the very last sentence or question is what will allow you to set that up. It says, do these data indicate that the percentage of wheat crop lost in hail in Weld County is different either way from the national mean of 11%? So they're telling us the null is 11%. That's what it's equal to. The alternate is, do we think it is different from that? Well, different from either way would be is not equal to. So in this case, we would put is not equal to 11%. And that would be, in this particular example, how you set up the null and the alternate hypothesis. All right. So step 1 is your hypothesis, which we just talked about. Now in step 2, we will calculate a statistical test. But before we do that, I want to talk about the alternate hypothesis. The alternate hypothesis is what dictates what type of a test that we are doing. If our alternate would be a less than statement, that would mean we have a left-tailed test, so the picture would look like this. So if the alternate hypothesis is a less than, you have a left-tailed test. If your alternate hypothesis is a greater than, you have a right-tailed test, so the picture would look like that. And then if your alternate hypothesis is not equal to, which is what we just experienced, then we have what is called a two-tailed test, and the picture would look like that. So be aware that the alternate hypothesis is what dictates less than left-tailed, greater than right-tailed, not equal to two-tailed. All right, so we've already talked about step 1, which is setting up the hypotheses, your null and your alternate. Step 2 is when we calculate what is called the test statistic. And this will be a z-value because sigma is known. If you remember, when sigma is known, we calculate a z-value. When sigma is unknown, we calculate a t-value. So in the examples we're going to be doing, sigma is given. So step 2, the test statistic will be a z-value. Now remember that the z tells you how many standard deviations away from mu, or the middle, that you are. Then step 3 then is calculating our p-value. Now I'm going to go through this, but if you are listening to me and you think, I'm not sure I quite understand, just hang on, because I think when we actually do an example, it will clarify it a lot. Okay, so step 3 is your probability value. Well, if our alternate was a less than and we had a left-tailed test, then we're going to do the probability that z is less than the value we calculated in step 2. If my alternate hypothesis is a greater than statement, if my alternate is a greater than, then I'm going to find the probability that z is greater than the test statistic. And remember, when it's a greater than, when you go to the table, you do 1 minus the number from the table. Now, the big difference is the to tell or the is not equal to. Because you're going to take the probability that z is less than the negative test statistic plus the probability that z is greater than the positive test statistic. So in step 2, you calculate a test statistic. Let's say we calculated positive 2.33. So over here we would have z is greater than positive 2.33. Over here we would have z is less than negative 2.33. Say in step 2, the test statistic, we calculated negative 1.25. So here we would do z is less than negative 1.25, and here we would do z is greater than positive 1.25. Okay, so again, when we do an exact example, I think it'll make more sense. Now, one thing that we have to consider in any type of test is sometimes errors can be made. And the example I always give is a pregnancy test. If you ever think you might be pregnant and you go to the store and you buy a pregnancy test, is that 100% accurate? Well, no, it's not. Sometimes mistakes can be made. Same thing with the statistical test. Now, in statistical tests, there are 2 types of errors. There's what we call a type 1 error and a type 2 error. The reason I have type 1 error underlined is because that's the only one we consider in this particular statistics class. Now, a type 1 error is when your null hypothesis is actually true, such as the average age of students is 35, and our tests lead us to reject it when in all reality it is true. That would be an error is being made. So what that means is we have to consider that possibility of that error. So we have to decide how willing are we to make that error. And this is called the probability of making the type 1 error. And this is also known as the level of significance, which the book will define it as alpha. Now, we will look at 1% or 5%. And again, just hang on when we actually do the tests. I think it will clarify it. Now, what this tells us is how often we're willing to make a mistake. Am I willing to make a mistake 1% of the time or 5% of the time? So that's the difference between alpha and p-value. Alpha is how often we're willing to make the mistake, and p-value will tell us the probability that we will make that error. So then that would lead us to step 4. And based upon comparing our p-value to alpha, we will either reject the null or fail to reject. So if my probability of making an error is smaller or equal to how willing we are to make an error, we reject the null and embrace the alternate. If the probability that I make an error is larger than how willing I am to make an error, then we fail to reject the null, which means we cannot embrace the alternate. And then step 5 is your conclusion, and on the conclusion for all the statistical tests that we do, when you reject the null, you have sufficient evidence. When you fail to reject, you have insufficient evidence. So now what I want to do is do some actual problems, because I know that we went through those steps. It's kind of a lot to absorb, but when you actually see them worked, I think it will make a lot more sense. So if you will get your book and turn to page 424 and look at number 19. Let X be a random variable representing dividend yield of Australian bank stocks. We assume it's normally distributed. They give me sigma. So right there, you have to go, okay, sigma is given, so I know my test statistic will be a z value, not a t value. A random sample of 10 is given. They give us the sample mean to be 5.38%. They tell us that sigma is 2.4%, and they tell me that mu is 4.7%. Now, to set up the null and the alternate, I'm going to look at the very last question. Do these data indicate that the dividend yield of all Australian bank stocks is higher than 4.7? So they're telling us the average of these is 4.7. So that is my null, mu is equal to 4.7%. Then, again, when I read that last question, it says, does it indicate that it is higher than? So my alternate is that it is greater than 4.7%. Now, since my alternate is greater than, then I know that tells me I have a right-tailed test. Okay, so there's my right-tailed test. Now, step 2 is calculating my test statistic, which is my z-value. So we're going to calculate this z-value right here. All right, so in order to do that, we're going to do z equals x bar, 5.38%, minus mu, 4.7%, divided by sigma, 2.4%, divided by the square root of n, which is 10. Now again, when you go to your calculator, just be careful that you correctly put in the parentheses here so you calculate it correctly on your calculator, because it stinks to miss points because of a miscalculation. And when you calculate and do normal rounding rules, you will get that this is z-value is 0.90. So that tells me the z-value is 0.90. Now, remember, in step 3, we're going to find the probability value. Since I have a greater than in my alternate, that means when I go to calculate my p-value, I'm going to calculate the probability that z is greater than, and it's greater than because the alternate hypothesis is greater than, and my z-value we calculated was 0.90. Now, anytime I have greater than, I know I'm going to do 1 minus the number that I find on the table. So you'll now go to your z table, and you're going to look up 0.90, and you're going to find 0.8159. Now, how we read the z table goes back to chapter 6, so I'm assuming that you still know how to do that. So when we subtract those, we get 0.1841. Now, what we've just calculated is the probability that we will make a type 1 error. So in step 4, we're going to compare the probability that we will make an error, which is 0.1841, or 18.41% of the time an error will be made, and we're going to compare that to alpha. Now, if you'll look in your book at the very end of problem number 19, it says use alpha of 0.01. Well, that's the same thing as 1%. So this is how often an error will be made. This is how often we're willing to make an error. This is greater than, so I go back to my step 4, and if it's ever greater than, then we fail to reject the null, which means I haven't proved that the null's still correct, but I have not proven that it's incorrect either. So we fail to reject it. We neglect to reject it. We cannot reject it at this time. So when we fail to reject, then in our conclusion, there is insufficient evidence at the 1% level of significance to conclude the average division yield is, and then it refers back to the alternate, and the alternate stated that greater than 4.7%. So there is not enough evidence, insufficient evidence at the 1% level of significance to conclude the average division yield is greater than 4.7%. Basically what we're saying is we have not proven that it's greater than. All right, so let's go and do another problem so you can get more familiar with this. So now on page 425, we're going to do problem number 23. Now this is the one we already set up earlier in the set of notes. This is the one about the wheat hail crop that is destroyed by hail. So we already set up earlier that on average it's 11%, And then it said for the alternate, different from, so this was is not equal to 11%. Now, this is the one that's quite different because the alternate is not equal to, then we have a two-tailed test. Now, typically when we had two z-values, we shaded in between them. But now in this chapter, we shade the tails. So when we get to the part where we calculate the probability, that is going to change how we find that number. Okay? All right. So if I gather the rest of the information given in the book, we already know that mu is equal to 11%. It tells me that x bar is 12.5%. We are given that sigma is 5%. Now again, since sigma is known, we will calculate z values. And our sample was 16 different wheat crops. Now, again, since sigma is known, I know I'm calculating a z value. So it is x bar 12.5 minus mu 11 divided by sigma 5 divided by the square root of n, which is 16. And once again, just be very careful in your calculator where you put your parentheses. And when you do that calculation, you should get 1.2. Now, notice we got positive 1.2, so z equals positive 1.2, but since we have an is not equal to, it's two-tail, this is symmetrical, so I automatically know this is negative 1.2. Now, step 3 is where you have to be careful. We need to find this probability, and that's the probability that z is less than negative 1.2. And that will take care of this part. And then we're going to add that to the probability that z is greater than positive 1.2. Now, one thing you need to realize is this is symmetrical. So these two areas, these two probabilities should be the same amount. So once you calculate one, all you have to do is double it. So go to your z table, find negative 1.20 on the z table, and you should find 0.115. Is that right? 0.1151. Sorry about that. So what we have just found is that this area right here is 0.1151. Now, since this is symmetrical, then this should be 0.1151. So at this point, you could just double it. But I do want to show you statistically how this works. Since this is greater than, now we're going to add these, but since this is greater than, then I would do 1 minus the value that I find out positive 1.20 on the table. And when you go to the z table, you will find 0.8849. And if you will subtract 1 minus 0.8849, you will get 0.1151. So we're going to add 0.1151 plus 0.1151, and that will give us 0.2302. Now, again, this is the amount, or how willing, or I'm sorry, not how willing, how often an error will be made. So we're going to compare that p-value, which is 0.2302, which is 23.02%. So this is telling me, based upon my numbers, that an error will be made 23.02% of the time. Well, that's making an error quite a bit of the time. And we're going to compare that to alpha. So I go back to the book, and it says use alpha of 0.01. or 1%. This is how willing I am to make a type 1 error. This is how often I'm going to make an error. So since this is greater than, we again will fail to reject the null hypothesis. So what that means is we cannot reject the null and embrace the alternate. We've absolutely, at this point, haven't proven anything. So when you fail to reject, there is insufficient, not enough evidence at the 1% level of significance to conclude the average crop lost to hail is, and then you always go back to your alternate, so is not equal to 11%. So that is that example. I want to do one more to hopefully help you feel like you have a handle on this. We're going to do number 21 on page 424. Bill Arthur is a zoologist who studies Anna's hummingbird. Suppose that in a remote part of the Grand Canyon, a random sample of 6 of these birds were caught, weighed, and released, and they give us each of those 6. So we are given that X bar is 3.75 grams. We are given that sigma is 0.7. It is known that for the population of all Anna's hummingbirds, the mean weight is 4.55 grams. So right there, they tell us mu, so I know the null is mu equals 4.55 grams. Then that very last question will allow me to find out what my alternate needs to be. Do the data indicate that the mean weight of these birds in this part of the Grand Canyon is less than? So in this case, mu is less than 4.55 is what we're trying to prove. Now, as soon as I see that this is less than, I know I have a left-tailed test. So now in step 2, I'm going to calculate, there we go. I'm going to calculate, since sigma is known, I'm going to calculate the z value, which will be 3.75 minus 4.55 divided by 0.7 divided by the square root of n, which is 6. And again, just be sure that you're putting your parentheses in the correct place. And when you do, your calculation should come out to, let's see, negative 2.8. So z is equal to negative 2.8 or negative 2.80. So that's our test statistic. So then we're going to take that test statistic, and since the alternate is less than and we have a left-tailed test, I know my probability value will be the probability that z is less than negative 2.8 or negative 2.80. And since it's less than, you just go to the table, find negative 2.80 and use that value, and you should find 0.0026. So now we're going to compare. The probability that we will make an error is 0.0026 or 0.26%, so less than 1%. We're going to compare that to alpha, which the book tells us that alpha is 0.01 or 1%, and 0.26% is less than. So since the probability of making an error is smaller than how willing we are to make the error, in this case, we reject the null. So what we have done is proven that the alternate is actually correct. So in this case, there is sufficient evidence at the 1% level of significance to conclude the average weight of Anna's hummingbirds is, and I go back to the alternate, less than 4.55 grams. So we have sufficient evidence to say it's changed. It's not equal. It is less than 4.55 grams. That is 8.1.